Hello students, in previous lecture we studied about stationary wave with their properties. In this lecture we are going to study derivation of stationary wave on straight string, comparison between stationary wave and progressive wave. Similarly, comparison between free and forced vibrations and terms like harmonics and overtone. We are starting with the derivation of stationary wave on a straight string. As we know, when two identical waves traveling along the same path but in opposite directions interfere with each other, the resultant wave is called stationary wave. Now, consider two simple harmonic progressive waves of equal amplitude A and wavelength lambda propagating on a long, uniform, straight string in opposite directions. The equation of wave traveling along the x-axis in the positive direction is y1 is equal to a sine 2 pi inside the bracket nt minus x upon lambda. Equation 1. The equation of wave traveling along the x-axis in the negative direction is y2 is equal to a sine 2 pi inside the bracket nt plus x upon lambda bracket close. Equation 2. By the principle of superposition of waves, the resultant displacement of these two waves is given by y is equal to y1 plus y2. Substituting equation 1 and 2 in the above equation, we may write y is equal to a sine 2 pi inside the bracket nt minus x upon lambda bracket close plus a sine 2 pi inside the bracket nt plus x upon lambda bracket close. By using the formula of sin C plus sin D, sin C plus sin D is equal to 2 sin inside the bracket C plus D upon 2 bracket close into cos C minus D upon 2. Then we may get y is equal to 2a sin 2 pi nt into cos 2 pi x upon lambda. That is, y is equal to 2a cos 2 pi x upon lambda into sin 2 pi nt. Let 2a cos 2 pi x upon lambda is equal to a. Therefore, the above equation will become y is equal to a sin 2 pi nt, where omega is equal to 2 pi n. Therefore, we get y is equal to a sin omega t. This is the equation of stationary wave, which gives resultant displacement due to two simple harmonic progressive waves. Condition for node and for antinode. Nodes are the points of minimum displacement. This is only possible if the amplitude is minimum, that is 0. As we know, the amplitude A is equal to 2a cos 2 pi x upon lambda. Here amplitude is 0. Therefore, we may write 2a cos 2 pi x upon lambda is equal to 0. Therefore, cos 2 pi x upon lambda is equal to 0. Now, the angles of cos are pi by 2, 3 pi by 2, 5 pi by 2 and so on, for which the value is 0. Therefore, by comparing the angles, we may write 2 pi x upon lambda is equal to pi by 2, 3 pi by 2, 5 pi by 2 and so on. If 2 pi x upon lambda is equal to pi by 2, then the value of x is equal to lambda by 4. If 2 pi x upon lambda is equal to 3 pi by 2, then the value of x will be 3 lambda by 4. If 2 pi x upon lambda is equal to 5 pi by 2, then we will get the value of x is 5 lambda by 4 and so on. Therefore, x is equal to, inside the bracket, 2p minus 1 bracket close lambda by 4, where p is equal to 1, 2, 3 and so on. The distance between two successive nodes is lambda by 2. Now, condition for antinode. Antinodes are the points of maximum displacement. That is, A is equal to plus or minus 2A. Therefore, 2A cos 2 pi x upon lambda is equal to plus or minus 2A. Therefore, cos 2 pi x upon lambda is equal to plus or minus 1. Here, we are again going to compare the angles of cos. Therefore, we may write 2 pi x upon lambda is equal to 0, pi, 2 pi, 3 pi. If we are comparing 2 pi x upon lambda with 0, then we will get the value of x is 0. If 2 pi x upon lambda is equal to pi, then the value of x will be lambda by 2. Similarly, if 2 pi x upon lambda is equal to 2 pi, then the value of x will be lambda and so on. Therefore, x is equal to lambda p upon 2, where p is equal to 0, 1, 2, 3 and so on. Here also, the distance between two successive antinodes is lambda by 2. Nodes and antinodes are formed alternately. Therefore, the distance between a node and an adjacent antinode is lambda by 4. The next article is the distinguish between progressive wave and stationary wave. So, you can write the first point is the definition of both the waves. A wave which is continuously traveling in the same direction in the same medium is called progressive wave. Whereas in a stationary wave, when two identical waves traveling along the same path but in opposite directions interfere with each other, the resultant wave is called stationary wave. Now the second point, the disturbance travels from one region to the other with some velocity, but in the stationary wave, disturbance remains in the region where it is produced. Therefore, the velocity of the wave is 0. The third point, amplitudes of all the particles are same in progressive wave, while amplitudes of the particles are different in stationary wave. Now the fourth point is, all the particles do not cross their mean positions simultaneously. But in the stationary wave, all the particles cross their mean position simultaneously. Fifth point, all the particles are moving in progressive wave. But in the stationary wave, all the particles except node are moving. Means the particles which are present at node positions are always at the rest. Now the last point, in the progressive wave, you may write about the energy. Energy will transferred from one region to another, while in stationary wave, there is no transfer of energy. Let us start the explanation about the terms free vibration and forced vibration. So, first we will see what is exactly meant by free vibration. If a body is capable of oscillation, displaced from its equilibrium position and released, then it starts oscillating or vibrating. This type of vibration is called free vibration. In free vibration, the body at first is given an initial displacement and the force is then withdrawn. The body starts vibrating and continues the motion on its own. No force, that is, no external force acts on the body further to keep it in the motion. The frequency of vibration of the body is called its natural frequency. For example, when a simple pendulum is pulled aside and released, it performs free vibrations with its natural frequency. Forced vibration. The definition of forced vibration is the vibration of body under the action of external periodic force, in which body vibrates with frequency equal to frequency of external periodic force other than its natural frequency, are called forced vibrations. In forced vibrations, an external periodic force is applied on a body whose natural period is different from the period of force. The body is made to vibrate with a frequency equal to that of externally impressed force. The amplitude of forced vibrations always depends upon the difference between the frequency of external periodic force and the natural frequency of the body. If this difference is small, the amplitude of forced vibrations is large and vice versa. If the frequencies are exactly match, it is termed as resonance, and the amplitude of vibration is maximum. The example of forced vibration is, if a periodic force is applied to a simple pendulum, then pendulum can be made to oscillate with different frequency. The oscillations then will be forced oscillations, and the frequency is driver frequency, or it is also called as forced frequency. The next article is harmonics and overtones. All the musical instruments produce sound, and that sound is a mixture of different frequencies. It contains low frequency sound as well as high frequency sound. This low frequency sound is called harmonics and high frequency sound is called as overtone. Now we will see what is meant by harmonic. The minimum frequency of a sound produced by a given musical instrument is called the fundamental frequency, or it is also called as first harmonic. Fundamental frequency is always denoted by letter small n. The term harmonic is used when the frequency is an integral multiple of fundamental frequency. For this, I am giving you one example. Suppose we are considering n as a fundamental frequency, or it is also called as first harmonic. If we are multiplying n by 2, then we will get second harmonic. If we are multiplying n by 3, then we will get third harmonic. In this way, if we are multiplying n by 29, then we will get 29th harmonic. The next term is overtones. The term overtone is used to represent higher frequencies of sound greater than the fundamental frequency. The first higher frequency after the fundamental frequency is called the first overtone. The next higher frequency is the second overtone, and so on. The overtones are only those multiples of fundamental frequency which are actually present in a given sound. To understand the concept of harmonics and overtones, I am giving you one example. As we know, the term harmonic is used when the frequency is an integral multiple of the fundamental frequency. So, let us consider n is equal to 100 Hz, that is nothing but fundamental frequency, or it is also called as first harmonics. Now, the second harmonic will become 2n, which is equal to 2 multiplied by 100 is equal to 200 Hz. Now, if we want fourth harmonic, so obviously 4 multiplied by n is equal to 4 into 100, that is equal to 400 Hz, and so on. Similarly, to understand the concept of overtone, as we know, the term overtone is used to represent higher frequencies of sound, that is greater than fundamental frequency. The first higher frequency after the fundamental frequency is called first overtone. Therefore, here n is equal to 100 Hz is the fundamental frequency. Now, when we are talking about the overtones, the frequency should be greater than fundamental frequency. Therefore, n1 is equal to 200 Hz will become as a first overtone. Now, n2, that is second overtone, which is equal to 300 Hz. Then if we want fourth overtone, that means phi n is equal to phi multiplied by 100, which is equal to 500 hertz. To understand the concept of overtone, we will see the case 2. In this case 2, I have given two frequencies, 200 Hz and 400 Hz, which are not actually present in the sound. Therefore, n is equal to 100 Hz is our fundamental frequency, and in case 2, n1 is equal to 300 Hz is the first frequency which is actually present in the sound. Therefore, it is considered as a first overtone. And next one, n2 is equal to 500 Hz, and this frequency is also present actually in the sound. Therefore, it is a second overtone. As we know, the overtones are only those multiples of fundamental frequency which are actually present in a given sound.